Last day of review before our final exam next Wednesday, the 21st of January. Of course, we have our extra help session Tuesday, the 20th, all afternoon. Go after school if we need to a little bit there. Yesterday, I gave you some real big hints on what's going to be on this exam, including a graphing question. I told you there will be a position time graph or a velocity time graph, and you're going to need to find out a whole bunch of things about that graph. Maybe what the position is, maybe what the displacement is, maybe what the acceleration is, and so on and so on and so on. So what I want to do here now, at the request of Carrie, is go over the graphing stuff. We'll go over two graphs, a position time graph and a velocity time graph, to cover all our bases, so that we know when we know going into the exam that we've reviewed the exact same thing that's going to be on the exam, whichever one it happens to be. Let's draw a line down the middle of the page and draw a position time graph on the left-hand side and a velocity time graph on the right-hand side. Now, on your exam, that should be labeled with the words position time, velocity time, because that's what we do in graphs, right? We don't put the symbols on. I'm just doing that to save a little bit of time and a little bit of energy here, okay? But on your exam, it'll say position time, velocity time. Now, that graph could take any one of a number of shapes. Let's go right there. There's my shape for my position time graph. And you know what? Let's do the same thing for my velocity time graph. Same shape. Let's put some numbers on here. Now, again, on your exam, there'll be more detail. It'll have a complete x-axis and a complete y-axis. I'm just going to put the relevant points on this one just to save a little bit of effort there. We're going to make this 10 seconds. We're going to make this 20 seconds. We're going to make this 30 seconds. Okay, we're going to make this 5 meters. We're going to make this 15 meters. And the units should be, I should have the units in there as well, right? Now, on this one, meters per second and seconds, let's make this one 10 seconds, 20 seconds, 30 seconds. And let's make this one 5 meters per second. And let's make this one 15 meters per second. These two graphs are exactly the same, right? No, they're not. There's one critical difference between these two graphs, and that's what the y-axis is. It changes everything. The numbers are the same, the shapes are the same, everything else is the same except what you see on the y-axis, but that's enough to change everything. All right, let's go through both of these. Let's say I want to find the position. Question number 1. Find the position at 7 seconds. How am I going to do that? Louis, go ahead. Go up and over, right. Go from 7 seconds, which appears to be about right here, go up and over. That appears to be about, pretty hard to tell on this graph with the way I have it drawn, but it would be about 12 meters, right? On your exam next Wednesday, you're going to have graph paper superimposed behind it, so you'll be able to tell a lot closer where it actually is. You don't need to estimate like you have here. Okay, it's going to be about 12 meters. Let's find the displacement between 0 and 10 seconds. How do we define displacement? Forget about finding it on the graph right now. What's the definition of displacement? You got a position. Displacement is simply the change in position. We did that the very first day of Physics 20, right? The change in position. So what's the change in position between 0 and 10 seconds here? Well, the position at 0 seconds is 5. The position at 10 seconds is 15. So the change in position would be 10 meters. It's final position minus initial position. All right, what's the velocity between 0 and 10 seconds? By the way, when you're writing this down, as I'm going through it here, don't just write down the answers. Okay, if something kind of jumps at you like, oh yeah, I kind of forgot that, make a little note. Make a little note about how I found that. So for instance, when I said that this was 10 meters, okay, and I said it was 15 meters minus 5 meters, beside question number 2, write a little note in another color or whatever that says, take final position up and over, initial position up and over, subtract them, or whatever you need to write down. in order to remember this for next Wednesday. The velocity between 0 and 10 seconds. Well, there's two ways of finding that. The velocity on a straight line graph can be found by the slope, or the velocity on the straight line graph can be found by v is equal to delta d over delta t. It amounts to be the same thing. The displacement between 0 and 10 seconds is 10 meters. The time between 0 and 10 is 10 seconds, so it would be 1.0 meters per second. It's our velocity between 0 and 10 seconds. What's the displacement between 20 and 30 seconds? Jordan, is your hand up? Sorry? It's 10. No, not between 20 and 30 seconds. It's not 10. That's the time interval between 20 and 30 seconds. What's the displacement between 20 and 30 seconds? Okay. No. No. What's the final position at 30 seconds? 0. What's the initial position, Stephanie, at 15 seconds? At 20 seconds. 15. What's the change? 0 minus 15 is negative 15. Right? It's final position minus initial position. Now you want to find the displacement between 20 and 30 seconds? Or sorry, the velocity? Well, it's going to be displacement over time, which is negative 15 meters divided by a time of 10 seconds, which gives me negative 1.5 meters per second. Hey, that negative is important, right? A negative slope means that it's going in the reverse direction, going backwards. How about the acceleration at 15 seconds? What's happening at 15 seconds? What's going on? Forget about answering this question right now about the acceleration. What's going on at 15 seconds? It's at rest. Okay, so Aiden, what's the acceleration at 15 seconds then? It's at rest. Right, 0 meters per second squared. What about the acceleration at 25 seconds? What's going on at 25 seconds? It's not at rest anymore, is it? It's moving. What do you know about the movement at 25 seconds? Yep. It's going to be a negative velocity because it's going backwards, right? But the velocity between 20 and 30 seconds, is that not a constant velocity? Straight line on a position time graph? If it's a constant velocity, what's the acceleration? Zach, what's the acceleration? No, that's the velocity is negative 1.5. The acceleration is 0. Good. It's constant velocity. How can it be a 0 meters per second squared when the line is clearly sloping downwards? Because that sloping downwards indicates velocity. The velocity is 1.5 here and here and here and here and here and here, the whole way down. If the velocity isn't changing, then Tyler, what's the acceleration if the velocity isn't changing? Right. Does that make sense? Just the same as it was in the second stage there at 15 seconds, the acceleration will be 0. Finally, one last question. Actually, 2 more questions. The displacement for the entire trip, or for the entire graph, the displacement will be, tell me this right now, quick. Bart? Negative 5 meters, because it's final position minus initial. Final is 0, initial is 5, so the displacement will be negative 5 meters. Good. And what about the average velocity for the entire trip? It changes, right? So we're going to find the average. The average velocity for the entire trip. Anybody have an idea how to find that one? Constant or average velocity is always found by delta d over delta t. Okay, that group A equation. The displacement over the entire trip is negative 5 meters. The time for the entire trip was 30 seconds. So we're going to say the average velocity is -5 divided by 30, which would be, I think, it's 0.167. Is that right? Somebody check that on the calculator. Negative 0.17 meters per second, I think. Yes? Okay, good, thank you. Well, we just found pretty much everything we can find for a position time graph. Can you do that? Think you can do that? Well, if the graph that you get on your exam, and there will be one on your exam, if it's a position time graph and you can do this, then you should get 100 on that question. Let's take a look at the velocity time graph now. The exact same shape of graph, the exact same numbers, but velocity on the y-axis instead of position on the y-axis. All right, let's start this. Let's find the velocity at 15 seconds. You want to find the position on a position time graph, go up and over. You want to find the velocity on a velocity time graph, you can do what? Up and over. So at 15 seconds, we're going to go up and over. It happens to be 15 meters per second. What about the velocity at, here's one for you. Should have made this the first one. The velocity at 7 seconds. Up and over, right? 7 seconds, up and over. Oh, lo and behold, it's 12. 12 meters? 12 meters per second. So again, you want to find position on position time graph, up and over. You want to find velocity on velocity time graph, up and over. What about the change in velocity between 0 and 10 seconds? Tiffany? Yeah, go ahead. Okay, we'll get to that. No, that's a good question, though. For the other one, Stephanie's question was, when you break up the graph into sections, what are we finding? I said, we'll get to that. She said, do you do that for the other graph at all? This one? No, never. For a position time graph, you will never break it up. If you get a position time graph on your exam, do not break it up into sections. There is no reason why you should do that. If you do that, then you're going down a wrong path. Okay, for a velocity time graph, you do have to do that. We'll get to that later on in some of the things we're going to find here. What's the change in velocity between 0 and 10 seconds? Okay, well, the final is 15, the initial is 5. Change in velocity would be 10 meters per second. What about the change in velocity between 20 and 30 seconds? Yep. It's just up and over, subtract the 2. So, I mean, logically think about it. Don't even try to memorize this. Think about it. The change in velocity. Well, what's the final velocity? 15. What's the initial velocity? 5. So let's subtract them to get the change there. It becomes 10 meters per second. So what is it? Ryan, what's the change in velocity between 20 and 30? No, that's the time, right? What's the change in velocity? What was the velocity at 20 seconds? 15. What's the velocity at 30 seconds? What's the change? Negative 15. What's the acceleration at 25 seconds? Well, in stage 3 at 25 seconds, the acceleration is constant everywhere between 20, Seth, the acceleration is the same everywhere along that stage there. Here, wherever. If we want to find the acceleration at 25 seconds right here, then that's the same as the acceleration, the average acceleration for the entire trip. Do not ever go v over t. For the first graph, d over t. Don't ever do that. Don't ever divide a y point by an x point. Divide a change in y by a change in x. So the acceleration, we can say, at 25 seconds is the same as the acceleration between 20 and 30 seconds. The change in velocity is negative 15 meters per second, and the time would be 10 seconds. So the acceleration would be negative 1.5 meters per second. In the last graph, the velocity was negative 1.5 because it was the slope of the graph. In this graph, the acceleration is negative 1.5 because it's the slope of the graph now. Yep. Yes, it is. Yeah, thank you. The velocity was 1.5 meters per second. Sorry, 15 meters per second. The acceleration is 1.5 meters per second squared. Thank you. And it is a negative as well. Now, Stephanie, here's one for you. What's the displacement? The total displacement? What do you think we're going to do? Break it up. So let's erase these lines here. Now let's break it up into sections, into recognizable sections here. Okay, that's not a shape that we recognize, so let's draw a little line across there. Let's draw a line across there. Section 1, 2, 3, 4. Now what do we got to do with the 4 sections? Yeah, get the area. So the area of section 1, that's the easy one because it's a rectangle. It's base times height. It's going to be 10 times the height of 5. So the area of section 1 is 50. Section 2, the base is once again 10, but it's a triangle, so it's a half of the base. 1/2 base times height. Base is 10. The height goes from 5 to 15, so the height would be 10 as well. That area is 50 meters as well, just by coincidence. The third section here, it's a rectangle, so it's base times height. The base is 10, the height is 15. So it's going to be base times height, 10 times 15 is 150 meters. And then finally, the final area is a triangle again, 1/2 base times height. The base is 10, the height is 15. So it's 1/2 of 10 times 15, which gives me 75 meters. Now, we want to find the total displacement, add them up. 50 plus 50 plus 150 plus 75 gives me 325, I think it is, isn't it? Now, finally, the last question I'm going to ask you is, what's the average velocity for the entire trip? Just like I asked you for question number 9 in the last one. The average velocity for the whole trip. It's the same as the last one. The average velocity was delta d over delta t. It's going to be, again, average velocity is always displacement over time. The displacement in the last case we found by just subtracting a couple numbers. Here we found it by taking the area. It's 325 divided by the time of 30 seconds. So that's going to give me, what, 325 divided by 30 is 10.8 meters per second. So look, we had 2 graphs. We're exactly the same shape, exactly the same numbers. One of them had an average velocity of negative 0.17. One of them had an average velocity of positive 10.8. Why such a difference? Because they're completely different graphs, even though they look the same. Positions on the y-axis, velocities on the y-axis. We deal with them differently. Who feels like they can ace this question on the exam? Get 100 on that question on the exam. Good, you better. Because you know exactly what you're going to see. Well, I shouldn't say that. You don't know exactly what you're going to see. It's going to be one of these 2 questions. Different shapes slightly and, you know, whatever. But I'm going to ask you the same things as I've asked you here today, either in blue or in green there. Okay? Listen, when we know what to expect, we can nail it, right? Again, I said yesterday, doesn't mean you shouldn't study other things. I told you basically what was going to be on 7 of the 10 questions. Doesn't mean you shouldn't study other things, because 30% of that exam, that rate of response is on other stuff. Study other things. But when you know this is going to be there, when you know for sure this is going to be there, then you better spend some time knowing this. Same with projectile motion yesterday. Same with vertical circular motion yesterday and whatever else we did yesterday. Yeah. You won't have one. No, you won't have one of those. Now, Jacob asked a question a few minutes ago as well. It was a lot less to it than what we've just done here, but we'll go over Jacob's question here now as well. Jacob's question related to the pendulum and the equation for the pendulum. Probably the second most awkward equation that we've done this year. Funny, they both appear in waves. The most awkward equation that we've done this year is probably that Doppler effect equation, right? But the good news is, the only thing we're going to have to rearrange in the Doppler effect is FD and FS. Okay, you're not going to have to rearrange for VW or VS. It's just too ugly. Okay, it's really, really ugly. So as much as that looks ugly, that equation, it's actually not that hard to rearrange. Okay. This one is the hardest one to rearrange. Now, Jacob, we may have to rearrange to solve for L. We may have to rearrange to solve for G. Let's try L first. Get rid of what's not attached. Well, everything's attached. So nothing to get rid of that's not attached. So what do we get rid of first? What disappears from this equation first? Yep. Divide by 2 pi. So it becomes T over 2 pi equals square root L over G. All right, good. Better. Still got a ways to go, though. Somebody else. What do we get rid of next? Tony? Right, we get rid of the square root by squaring it. It becomes T over 2 pi squared equals L over G. Now we're solving for L, right? You got to get rid of the G. It's the only other thing that's attached to the L. How do you get rid of that, Tony? We times it, right? So it becomes G times T over 2 pi squared equals L. There's my equation. Now let's solve for G now. You're going to notice that the first few steps in solving for G are the same as they were solving for L. But we'll go through them again anyways. Let's take the 2 pi over by dividing. T over 2 pi equals square root L over G. Let's square that. It becomes T over 2 pi squared equals L over G. And now let's take the G up by multiplying. Get L by itself. G times T over 2 pi squared equals L. Now, our purpose here wasn't to calculate L. Our purpose wasn't to rearrange for L. We just had to do that first because G has to be on the top. Solving for G, it's got to be on top. So that's the way we got it to the top, by solving for L. Okay. Now, this is where it kind of gets a little bit awkward here. We're going to take this entire term over by dividing because it's all multiplied by G. So G is equal to L over T over 2 times pi squared. Now, what you got to be careful of, in addition to rearranging this equation to solve for G, is plugging the numbers into your calculator. It can be a little bit awkward there too. Let's take this equation and plug a couple numbers in. Let's say that L is 1 meter, and let's say that T is, let's make it 2 seconds, okay? Okay. Now, follow along, please, on the calculator. Make sure you can do this. I'll actually sub those numbers in and then do it on the calculator. So it becomes G equals 1 over 2 over 2 pi squared. Again, follow along on the calculator, please. Unless you're really good with brackets and really comfortable with the calculator, please do it in steps like I'm about to do it. Get the number on the bottom first. 2 times pi equals. Get that number. Press equals. And then say 2 divided by that number. 2 over that number is 0.318. Then square it. So do what's on the bottom, then do what's inside the brackets, and then square it. So now I got this number here circled in black there, is 0.101. Now all we're going to do is say that top number 1 divided by that bottom number, 0.101, ends up being equal to 9.86 or 9.87. So G in this case, 9.9 meters per second squared. Is that okay? Jacob, is that good? Another question here, Kepler's constant that Ali's asking about. Ali, the good news is for this, we don't have to be able to do anything mathematically for this. It's just more of a concept we do. You can solve it mathematically. We just don't need to, that's all. So basically, Kepler's third law. Kepler's third law called the law of periods. And the law of periods says, in words, it says the square of the time, the average time of revolution around the central body divided by the cube of the average radius of revolution is equal to a constant. Well, what sense does that make? Okay, well, let's write it down to hopefully make a little bit more sense to you. Let's say we're revolving around the sun. Okay, we're revolving around the sun. Here's Earth revolving around the sun. If you take the square of the period of the Earth around the sun, which is a year, right? Just over a year, actually. Divide it by the average radius of revolution cubed of the Earth around the sun. You get a certain number that we're going to call K. In fact, we'll call it KS. It's not Kepler's constant for the Earth, even though we're using data about the Earth. It's Kepler's constant for the sun, because the sun is what's being revolved around. Okay. Now let's take another planet, Mars. We'll stick with the inner planets as opposed to going to those outer planets, because you know what happens when we get to those outer planets, right? Mars, the average period of revolution of Mars around the sun squared divided by the average radius of revolution of Mars around the sun cubed is equal to a constant called Kepler's constant for the sun. And those two numbers are exactly the same. Even though we use data for the Earth, data for Mars, those two numbers are exactly the same. Now, let's say we're talking about some other planet that, or some other star that we're going to call star X. Okay? Whatever that is, right? Star X. If you got planet 1 revolving around star X, then we could find that constant by saying T1 squared over R1 squared cubed equals K. But it wouldn't be K for the sun, it would be K for X. Okay, same deal over here. For planet 2 around star X, we'd say T2 squared over R2 cubed equals KX. So again, Kepler's constant for star X is the same regardless of whether you use planet 1 or planet 2's data. What does that really tell us? Well, what it allows us to do is calculate data about one planet given data about the other planet. So for instance, we calculate Kepler's constant for the sun using data for the Earth. Then, we don't know much about Mars because we're not on Mars. Hey, but we know how long it takes Mars to go around the sun. Knowing K that we figured out from the Earth, right? And knowing how long it takes Mars to go around the sun, we could calculate the radius of Mars's revolution around the sun. Make sense? Okay. One more question here about static friction and kinetic friction. Now, static friction is the friction that keeps an object from beginning to move, right? And kinetic friction is the force of friction that acts on an object when it moves. So here's the deal. You've got to know what kind of friction you're dealing with to determine what the value is. There are two equations. There's the force of static friction, max, not force of static friction, the max force of static friction, because when you calculate this value, it's not necessarily the actual value of friction, it's the maximum possible value of friction before the object begins to move. On the other hand, there is an equation, the force of kinetic friction, which once an object is moving, it is this value. It's not maximum this value, it is this value. So when it's not moving, it's this value or something less than this value. When it is moving, it is this value, or whatever that works out to be. So here's the thing. You got to find out whether it's moving or not. You got to find out whether it moves or not to determine what kinetic friction is or static friction is, or whatever the case may be. So let's do this. Let's first calculate the max force of static friction. Get that maximum value of static friction. Let's say it worked out to be, I'm going to write down a number here. Obviously, in each question it's going to be different. Let's say we calculated it to be 30 newtons. Look at your applied force. Look at how hard you're pushing it. If the force you push it is bigger than the max force of static friction, then it moves. Easy question. Okay, if it's bigger than 30 newtons, then this is your force of friction. Right? If it's smaller than 30 newtons, then this is not your force of friction. If you only push it with 10, that's your force of friction, 10. If you push it with 20, that's your force of friction, 20. You push it with 29, that's your force of friction, 29. You push it with 31, okay, you're back to kinetic friction because it's moving. You better calculate that value and see what it is. Does that make sense?